Okay, so in today's video, we're going to talk about the simple harmonic motion of a physical pendulum. So the major difference between a physical pendulum and a simple pendulum is in the mass distribution. A simple pendulum is one where all of the mass is basically concentrated at one point, and the mass of the connecting, string or rope can be completely ignored. A physical pendulum, on the other hand, has real dimensions and mass distributed throughout, so it could be any rigid object. Now, for our purposes today, I'm going to draw that object as a bar. It doesn't have to be a bar, it can be any object with mass, but let's suppose we have an axis at this point, and we draw a bar that's hanging from that pivot point. And let's assume that we know the center of mass of that bar is at this location here. So here's the center of mass. And it doesn't have to be a uniform object either. If it's a uniform object, then the center of mass is going to be halfway along its length, but it doesn't have to be. In this case, let's call the distance from the center of mass to the axis. We're going to call that distance d. And we've taken this bar and we've pulled it back to an angle theta from the vertical, like so. And we're going to allow it to swing in an arc in this direction. Okay, so since it's moving in an angular fashion, we're going to look at this from the perspective of torque. So what I'm going to say is that the moment of inertia of this bar times the angular acceleration is equal to the net amount of torque that's acting on it. Now, if we pull that bar back and release it, the only torque that's acting about that axis is gravity. So we could say I times alpha is equal to the torque from gravity. Well, gravity is going to pull down on the center of mass with the force equal to mg. The torque from that force is going to be mg times the distance from there to the axis, which is d, times the sine of the angle between those, which is just going to be sine of theta. And since theta is measured, in this case, clockwise from the vertical, and the torque is going to be counterclockwise, we're going to put a minus sign in this. So we'll have a minus sign here. Okay. We know that the angular acceleration is the second derivative of theta. So we can write this way as the second derivative of theta. Now you'll notice that this is looking pretty similar to the simple pendulum that we talked about before. I'm going to divide both sides by I. So I get this expression. So we have a situation where the second derivative of theta depends on the sine of theta. What we saw with the simple pendulum is that if theta is sufficiently small, and we said, somewhere between 0 to about 15 degrees, then sine of theta in radians is approximately equal to theta in radians. So when I say 0 to 15 degrees, again, go back and think about that. In terms of radians, you're talking about from 0 to pi over 12 in radians. Okay. So if sine of theta is approximately equal to theta, we end up with this. And this looks pretty familiar to what we did with simple harmonic motion for a simple pendulum. If we were to say that we could define omega squared equals mgd over I, then we could say second derivative of theta with respect to time equals negative omega squared times theta. And we've seen this differential equation many times before. We know that the solution to this differential equation is the function theta of t equals a cosine omega t plus b. So we prove that this is simple harmonic motion as long as the angles are small, just like the simple pendulum, even though the mass is distributed throughout the object. If we know where its center of mass is, and we know how far that center of mass is from the axis, and we can calculate its moment of inertia, then we can do that. Also, since the omega squared is mgd over I, we could say period of anything moving in simple harmonic motion is 2 pi over omega. So that's going to give us 2 pi over the square root of mgd over I. And we can rewrite that as 2 pi times the square root of I over mgd. Now if you look at that, it kind of makes sense. The higher the inertia, the longer the period is going to be, which would make sense. It's going to be harder to swing back and forth about an axis if it has a higher inertia. So think about that and how you can apply that, and experimentally how the moment of inertia will relate to the period of the pendulum, because a lot of times in the AP tests they'll talk about, experimental data and how we could analyze it to come up with the moment of inertia or something like that.